we can generalize this FIRE process, for fault identification process further by considering the cases like conflict on a single line like B equal to 0 and B equal to 1. So, if one particular line requires both of them, then this is for a single line, that is a conflict. So, that can be removed, those type of faults. Similarly, if we have got flip flops, so we have not discussed about sequential ATPGs, but sequential ATPGs are also there, and though the algorithms are a bit complex compared to this combinational ATPG, but in that case also, so we can avoid some of the combinations, like say suppose I have got 3 flip flops X, Y and Z. Now, it may so happen that due to in the operation of the circuit, in the operation of the application, so this X equal to 1, Y equal to 0 and Z equal to 1 is illegal. So, this can happen because this X, Y, Z, they are flip flops. So, they are a combination of them represent some state of the system that it models. Now, maybe some of the states of the system are illegal. So, the system will never go to those states. Now, if a test generation process requires that X should be set to equal to 1 and Y equal to 0 and Z equal to 1. So, in reality, we will never be able to force those flip flops to those values. So, any fault that requires this particular setting, so they are untestable fault, because we will never be able to put these values onto those flip flops. So, this is another way of finding out the untestable faults, particularly suitable for sequential circuits. Now, of course, for scan circuit this is not a problem. Scan circuit can always put X equal to 1, Y equal to 0, Z equal to 1. So, that is why this is not there in combinational and scan circuits, but for sequential ATPG this may be an untestable fault. Sometimes we need to proceed with multi-line conflict, like say this one, say this is an AND gate, A equal to 0, C equal to 1 is illegal, okay, because this is if I set A equal to 0, so I cannot get C equal to 1. So, if I find implication of A equal to 0, I will get C equal to 0 as a point. So, C equal to 0 and C equal to 1, that is a conflict. So, it can be found by the single line conflict. On the other hand, if I have B equal to 0, C equal to 1, so that is also a conflict. So, because this cannot be done. However, A equal to 1, B equal to 1, C equal to 0. So, this cannot be done by a single line conflict, because this S0 is the set of faults not detectable with signal A equal to 0. So, that is the set S0. Similarly, S1 is the set of faults that are not detectable with B equal to 0. Now, S2 is the set of faults not detectable under when signal C equal to 1. So, if we take intersection of these 3 sets, that will give us the untestable fault due to this multi-line conflict. So, A equal to 1, B equal to 1, C equal to 0 is a multi-line conflict which is not covered by the single line conflict. So, if you just take the intersection of these, so you will only get C equal to 1. So, you will not get this other fault A equal to 1, B equal to 1, C equal to 0. So, that way this will come only when you have taken the intersection of these 3 sets S0, S1 and S2. So, this way this multi-line conflict can also be used for determining the faults which are untestable. Can extend from the previous concept further, like consider say H equal to 1, G equal to 1 and Z equal to 0, H equal to 1, G equal to 1 and Z equal to 0. So, it is a multi-line conflict. So, we can extend these values as far as possible, like if we do the implication, backward implication and all that. So, we will get F equal to 1, C equal to 1, D equal to 0, E equal to 0, Z equal to 0. So, by extending the conflicts that are occurring here, so we can see that these are the further conflicts that can come. So, this is also a multi-line conflict. So, if we can if we start with one multi-line conflict and try to find the logic implications of that, then we can find further multi-line conflicts. So, that is also very much useful in detecting the untestable faults. So, to summarize this untestable fault identification part, so first we compute static logic implications. So, that is the first step. Then we compute untestable faults based on single line conflicts. Then we compute untestable faults based on multi-line conflicts, and then we remove all identified untestable faults from the list. So, by doing these first 3 steps, so we could find the set of untestable faults. Then before submitting the faults to the ATPG tool, to generate test pattern. So, we remove all those faults from the list of faults given to the tool. So, that way this ATPG algorithm will have much less number of faults for which it has to generate the test patterns. So, that will speed up the operation of the ATPG. Another class of ATPG algorithm, they are known as simulation based ATPG techniques. So far whatever technique we have discussed, so one of them was the exact method like Boolean difference. Then we have seen a number of heuristic methods, so like D algorithm, PODEM, FAN, etc. Now, another class of ATPG algorithms, so they are known as simulation based ATPG algorithms. So, the random and weighted random test pattern generators are the simplest forms of simulation based ATPGs, because they are generating some random pattern, doing a circuit simulation to see what are the faults it can detect, and if it detects a new fault, fine, otherwise it will generate another next random pattern. So, that is the simplest type. Now, this random generation process, so if we can guide it, so if we can guide this random generation process so that it can search, it can generate effective vectors. So, instead of being totally random, so if we can guide it to go to the portion of the search space where it needs to really generate new test patterns to improve fault coverage, then it is very much useful. At the same time, computation cost should be low. So, it is not that this exploration process takes a lot of time, and the test set generated should also be small, the compact test set. So, these are actually the desirable features. So, if we can do this thing, then we can come up with some good ATPG technique. One of the very well known ATPG algorithms, class of algorithms, so they are based on genetic algorithms. So, genetic algorithms, we know that this is a stochastic optimization process that mimics the behavior of natural selection and this generations of how the generation improves, the quality of population improves. So, it is based on that. So, in case of this genetic algorithm, so any genetic algorithm is made up of these components, a population of individuals which we call chromosomes, and each individual is a candidate solution. Now, you see that for a particular problem, it may be very difficult to tell what is the optimum solution, but it may be very easy to give any arbitrary solution. For example, even for test pattern generation problem, so if you ask me to give a test pattern which detects a very high number of faults, very large number of faults, it is very difficult to give such a pattern. But if you ask me to give any test pattern, then I can give it very easily. So, I can just say any random in 0 1 binary sequence given to the inputs of the circuit. So, that itself is a test pattern, it will detect at least some faults or the other. So, hopefully. So, that is why, so this is each individual is a candidate solution. So, it may be possible that I can give a large number of such individual solutions without bothering about the quality of them. After that, each individual has an associated fitness. So, fitness actually tells how good or bad is the particular solution or the particular individual. So, in the context of test pattern generation, so if a pattern can detect large number of faults, so we can say that its fitness is high. On the other hand, if it detects only few of the undetected faults, then its quality is low, and if it detects none, then of course its quality is very bad. Now, so that way we can think about this test pattern generation process as a collection of individuals, where every pattern is an individual and they have got their fitness. Now, genetic operators, they evolve from one generation to the next. So, this will help us from the current generation. So, if we want to go to the next generation by generating new population or new individuals. So, they are done by three mechanisms. One is called selection, another is called crossover, another is called mutation. So, these are the three operators, genetic operators, that are used for evolving over the generations. So, in generation 0, so this is a pictorial description of this genetic algorithm process. So, in generation 0 we have got this individual. So, there are n individuals, and each individual here is a sequence of bit stream. Okay. So, each of them goes through a fitness evaluation. So, every individual has got some fitness measure associated with it. Now, there are three operators, as we have said. the selection, crossover and mutation. So, based on these fitness values of these individuals that we have in generation 0, these 3 operators, it will create new population. It may select some of them from this existing population, or it may generate some new population, and accordingly it comes to generation 1. Now, the point is that population size over the generation, they remain unaltered. So, here it was n, in generation 1 also it is n, in successive generations also it will be n. So, this actually mimics the behavior of natural genetics, but in natural genetics the advantage is that the population size is virtually infinite, whereas in case of this computer based simulation for these genetic algorithms, the population size is not infinite due to the limitation on the memory space, due to the limitation of the computational time. So, naturally we have to we do not get the level of variation that you can have in the nature, but if the population size is reasonably good, then we will be able to get good variation in the population, and possibly it will lead to better offsprings. So, this is the pseudo code of this GA based ATPG techniques. So, initially test set is null, and while there is improvement. So, improvement may be in terms of fault coverage, like new faults getting detected. So, fault coverage of the test set is improving. So, initially fault coverage is 0. So, what we do, initialize a random GA current population. So, initially it is randomly done, we compute the fitness of current population. So, for all the individuals we compute the fitness. So, fitness computation can be done by doing a fault simulation for individual patterns, the faults that are they are detecting, and then finding out the what is the overall population, what is the overall quality of the solution. Okay. Then for I equal to 1 to maximum number of generations. So, we have got some variable maximum generations. So, that tells for how many generations my GA will run. So, as I have already said, in nature the process is infinite. So, the population goes on evolving over generations, and there is no limit to the number of generations to which this population will evolve. But in case of computer programs, so we have limitations. So, we cannot run it infinitely. So, we put a limitation on the maximum number of generations for which the evolution will take place. So, what we do, add the best individual to test set T. So, we initially in generation 0, so we have generated one random population set. Now, from the random population set, after computing fitness, we get the best fit individual. That best fit individual is added to the test set T. So, T is now having one individual or one chromosome in it. Then we compute another set next population. So, this set is initialized to null, and then what we do, we try to create new population, new individuals to put into the next population set. So, what is done? We select two parents, parent 1 and parent 2 from the current population, and then perform crossover operator crossover operation over this parent 1 and parent 2 to create two children, child 1 and child 2. Then we do some mutation operation. So, both this child 1 and child 2, they are subjected to some mutation operation, and that modifies this child 1 and child 2 a bit, and then this child 1 and child 2, they are put into the next population. So, next population gets this thing. So, this process goes on. Okay. So, after we have, so for every iteration of this J loop, so we are generating two such child process, two such children individuals. So, after this J iteration is over, so we have got created populations equal to the population size. The next population has got population size number of individuals. So, again we compute the next population, and current population is updated to next population. So, then this process continues. So, again, so this for loop is over. So, this next generation, the generation it comes starts with the next generation, and this process goes on. And while there are improvement, means while there are improvement in the say the fitness, if say the fault coverage. Okay. So, that may be a fitness measure. Now, the selection operator. Now, as we have said, is in this case say this crossover and mutation. So, when we are doing this thing, so there is a selection process of parent 1 and parent 2 from the current population. Now, this how do we select? Like if I have got say n number of individuals, so we can randomly select two parent from there. But a general observation is that if the parent individuals have got good fitness, then the children individuals will also have good fitness. That is a general observation. Okay, so that's why how to do this thing? This selection process can be made using two different technique. One is called Rowlett wheel selection, another is called tournament selection. In Rowlett wheel selection, what is done is that these individuals 1 to n, they are put on a Rowlett wheel. Now, depending upon the fitness of individuals that we have, so it is assigned a range of values in this Rowlett wheel. So, in this particular case, say the individual 6 has the largest fitness. So, it is given this much of region of the Rowlett wheel. Similarly, 2 is the next one. So, 2 is given the next region of the Rowlett wheel. So, that way they are given individual regions of the Rowlett wheel. So, if this Rowlett wheel is rotated, then the possibility of selecting 6 is the highest, then possibility of then followed by selection of 2, selection of 5, like that. So, in a random number generation process, so we can mimic this behavior of Rowlett wheel. So, if we can divide this random number range into different sub ranges, and the sub range, a larger sub range is allocated to individuals that have got better fitness. Okay. So, and now a random number will be uniformly generated, and then whichever range it falls, whichever sub range it falls, based on that the corresponding individual will get selected. So, the possibility of selecting better individuals will be higher in case of this Rowlett wheel case. Another selection process is known as tournament selection. So, tournament selection is like this, that it's between two individuals. So, you randomly select two individuals from the population. Now, whichever is better, so that wins. That one is finally selected. So, for example, if it picks up individual 1 and 5, and 5's fitness is better than 1, then individual 5 qualifies for the crossover operator. The same process is now repeated for selecting another individual. So, again there is a tournament between two randomly picked up individuals, and whichever individual wins, so that will take part in crossover along with the individual 5 that is selected before. So, this is the tournament selection. So, in both the cases either by the Rowlett wheel or tournament selection, so the parent chromosomes or parent individuals, they are getting selected. Now, the crossover operator. So, there are different versions of this crossover operator that are followed. Like first one may be 1 point crossover. So, this is one individual and this is the second individual, two parents. Now, suppose the crossover is at this point. So, what happens in the child, in the first child? So, the first part of parent 1 is copied and the second part of parent 2 is copied into this. So, you see the first part of parent 1 and second part of parent 2 forms the child 1. Similarly, second part of parent 2 followed by first part of child 1 forms the child 2. So, this is for 1 point crossover. So, there may be 2 point crossover, like over this length of the individual. So, you can select 2 points along which the crossover will take place, and now it is the first part from the first individual, second part from the second individual, and third part from the first individual. So, that forms the first child. Similarly, first part from second individual, second part from first individual, and the third part from second individual, that forms the second child. So, this way this 2 point crossover. So, in this can be generalized. So, it can go to any point crossover that we can look for, and in the most generalized case, we can prepare a mask. Okay. So, in this, suppose this is the mask that is generated. Now, in this mask, if the bit is 0, then say we will copy child 1 from parent 1 and copy child 2 from parent 2. On the other hand, if this mask is 1, mask bit is 1, so we will copy parent 2, we will copy this copy parent 2 value into child 1 and parent 1 value into child 2. So, this is just the reverse. So, this is for individual points based on this mask. So, these bits will get selected, and that way that will define another type of crossover. So, it is a number of points at which crossover is taking place is much higher compared to the 1 point or 2 point crossovers that we have seen. So, this is also known as uniform crossover. The mutation operator. So, mutation operator, so what happens is that if you just go on doing crossover, so since the varieties are what we have in the population only. So, the individuals, they are the varieties that we have. Now, it does not import any new variety into the system. So, if we just have the crossover operator. So, a better operator for this purpose is the mutation operator. So, in mutation operation, what it does, it randomly flips a bit position. Okay. So, it in a chromosome or in an individual, it will randomly flip one particular bit. So, that will bring variety which was not present in the population so far. So, that will be taking the thing. So, it is necessary to keep mutation rate small, so that search will not seem randomized. So, if the mutation rate is high, then it shows random behavior, because randomly a large number of bits will change. So, that is more of a random search, this is not a directed search, but what we are looking for is that two good individuals, so they will give rise to good children. So, that way that the search is being directed by the genetic algorithm. So, if you increase mutation rate high, you make mutation rate high, then that philosophy will be lost. Okay, that will become more of a random behavior. At the same time, when we are in nature, actually this mutation rate is very small. So, it is very unlikely that all on a sudden one gene of a chromosome will change. So, it changes over say large number of generations. However, in case of computer programs, so it may be that we keep this mutation rate a bit high compared to this natural genetics, because the population size is limited. So, we must keep the size as a factor, this mutation rate at a factor. Now, how do we choose a population size? Like what should be a population size? So, it says that it should be a function of the individual size. So, it depends on the whatever is the individual size, because individual size will tell us what is the total search space size, and out of that search space we should be putting a part of it into the population. So, if larger the individuals, they will require larger population to allow reasonable diversity. And again for this test generation problem, the size depends on the number of primary inputs of the circuit, because every individual is nothing but a test pattern, and a test pattern size is equal to the number of primary inputs of the circuit. So, if the circuit is if the number of inputs in a circuit is large, then naturally this input size, this individual size also has to be large, and accordingly to bring large number of variations, the population size also needs to be large. So, that is one potential problem of this particular approach, because we need to have large population for larger circuits. For sequential circuits, an individual may be a sequence of vectors, because in sequential circuits what happens is that we need to apply the test patterns in a sequence. The first pattern will put the flip flops in some proper state, and the second pattern will do the actual testing. So, that way we need to have some sequence of vectors. So, the sequence of vectors is a problem. So, this the individual that we are talking about, so that is basically a sequence of vectors. Sometimes we encourage generation gap. What it says is that some individuals may be carried over from one generation to the next. So, the algorithm that we have seen, it says that from current generation to the next generation, so the population generation process is by means of crossover and mutation operator. But it may so happen in the process that some good chromosome which was present in this generation get lost when it comes to the when we generate the next generation population through crossover and mutation operators. So, what is desirable is if some individuals are really good, so they may be directly copied to the next generation. So, they do not go through this crossover mutation channel, they directly get copied onto the next generation. So, this creates a generation gap in the evolution process, but that may have to be encouraged. How many generations that we run a GA? So, again it is related to population size. So, larger the population, so we should it will demand more number of generation. So, basically what happens is that if you look into this, if you just look into the operation of any genetic algorithm, so this side we have got the generations, and this side we plot the say the best fitness or average fitness, whatever average fitness of individuals. then we will see that for the first few generations, so it will start coming, it will be improving very fast, but after that this improvement rate becomes more or less flat, and again after some time it will decrease a bit, and then it will go like this. So what happens is that for large number of generations in between, like say this region, so the quality does not improve. Similarly, in this region quality does not improve. So that can happen. So we have to take those things into consideration. Okay, so we have to see that okay, those parts are taken care of. So until and unless we make our, so after this, if there is a drop, so if we are not allowing to the GA to run up to this generation, so this particular solution will not be obtained. So this problem is there. So as a result, larger the population size, larger will be this generation that will require to run. Okay, so larger population will demand more generation, and the generation gap will affect the number of generations needed to reach a satisfactory solution. So that is also a factor, because so that how many chromosomes you are directly copying from one generation to the next generation. And actually, when do we terminate? One termination is of course the maximum number of generations that we can allow the GA to run. Another termination is that okay, if the best solution does not improve over last few generations, then we can say that okay, possibly we have reached a good solution, and we stop at that point. So that can be done. About the fitness function, so it measures the quality of the individual, essential for a GA to converge to a solution. So fitness function, it should be good, it should reflect the actual fitness of the individuals. So for this test pattern generation problem, so we can have several such fitness functions, like number of faults detected by the individual. So that is one type of fitness function. Then number of faults excited by the individual, so that is also, that may also be a fitness function. Number of flip flops set to a specified value. For sequential ATPG, this is important. The number of flip flops set to some specified value, so that may be another fitness function. Or we may have a weighted sum of these factors. So when we go to some other test pattern generation technique, like say power hour testing and all that, so we may find that okay, we have to have some other factors to come in the fitness function. So this fitness function is very important, and this has to be chosen carefully. We will continue in the next class.